Swayam Prabha. Digital India. Educated India.
Okay, we'll start. So the last lecture I was talking about some tutorial problems. So despite being very careful with the notations, I still made a mistake. So instructors are not always infallible. One student came back to me after the class and pointed out this mistake. So the mistake is that in the first problem, the overall coefficient is not KL, this should be KX. Okay, that's the notation we are being used. So you may want to correct that. So the overall liquid phase mass transfer coefficient is capital K with the suffix of X. And then similar mistake was there in problem 5. I think there was this KL that should have been KX. Okay, so you may want to correct these two places. Okay, so like I was saying, the capital Kx is the overall liquid phase mass transfer coefficient when the concentrations are expressed in mole fractions. KL is used when the concentrations are expressed in molar quantities, like molarities, moles per unit volume. Okay, so in this class we are going to look at material balances. So doing mass balance is something is familiar to you. You might have done this in other courses. So material balance is nothing but mass balance. When there is a solute exchanging between two phases at two different points, so the mass balance have to be satisfied. Mass should be conserved. So that's what mass balance is. Okay, this is something you might have already done it. We are going to revisit this again because the way we are going to do mass balance in mass transfer equipment is slightly different because of the way that we use this concentrations and different types of operations, co-current, counter-current, cross-current, etc. So we're going to take a look at these material balance again and then write very specific to the mass transfer operations. Okay. In some way you will see a semblance to the heat transfer problem when you do co-current, counter-current heat exchange. You might have done this in terms of energy balances. Okay, so now this is an equivalent of that, but we are going to do mass balance because of solute transferring from one phase to the other phase. So before I do that, I want to kind of recollect the discussion that we had about let's say in a wetted wall column. Okay, so a wetted wall column is basically a very simple cylindrical tube. So some reservoir of liquid is here. Small liquid forms a film and then flows down the column because of gravity. So this is liquid in and here is liquid out, and the gas is sent from the bottom and then leaves at the top. This is gas in, this is gas in, this is gas out. So here when this gas containing some solute, okay, again you can take an example of ammonia air mixture as a gas phase, and then when it goes through the column, this ammonia is actually absorbed by this liquid water here because of this close contact between the gas and liquid. Okay, this is something we already seen. It's a very simple apparatus to study absorption. So if I look at any particular location in this particular equipment, we talked about the concentrations, equilibrium line, and driving force line, etc. So suppose if I say Y is the composition of the solute in the gas phase and X in the liquid phase, there is an equilibrium line. Okay, so this is the equilibrium line. So at any point here, if I take the measurement of Y and X, you may see that that point may be located at this point P, and because of the flow of the two phases and there is an associated mass transfer coefficient, you have a liquid phase and you have a gas phase film coefficients, and we did a mass balance and then we showed that there is a line with a slope minus kx by ky. So this YAG is the concentration of the bulk composition and XAL is the composition in the liquid, and there is a corresponding interfacial concentrations. This is YAI, this is XAI. So what this basically means is, if I take any one point in this equipment, there is a corresponding bulk phase composition which is not at equilibrium. Okay, it is far away from the equilibrium, but we know exactly how this bulk concentrations and interfacial concentrations are related. Okay, when I say interfacial concentration, I am equally denoting them as equilibrium concentrations. Interfacial concentrations, equilibrium concentrations are one and the same. Okay, we talked about this before. So the interfacial concentration can be located on the equilibrium line. Okay, so basically there is a driving force for mass transfer in the gas phase equivalent to YAG minus YI. That's the driving force for the gas phase mass transfer, whereas this XAL minus XAI is the driving force for the liquid phase mass transfer. Okay, and this slope depends on how you are going to design your mass transfer equipment so as to have a particular Kx Ky value. Okay, so as a chemical engineer, we have options to change the operation such a way that the Kx Ky can be manipulated. You can make one of them larger than the other or improve both of them. Okay, so that is to do with how you construct this column, which kind of flow is going to be there. Okay, so based on these operating conditions, we can change Kx Ky. Those are the mass transfer coefficients. So this is something very important because you have to understand this equilibrium line and this is a driving force line, which are important for mass transfer. Okay, this is called driving force line. Okay, so I may call in the future as this is a DL, this is like EL. Okay, EL means equilibrium line, DL means driving force line. Is it clear to you? I mean, do you have any questions? This should be very clear because from here onwards, I'm going to have a little bit more complicated analysis. So it's very important that you understand what this point means, what this line means, and what controls the slope of the line and what's the equilibrium line. All this should be absolutely clear for us to follow the subsequent discussions. Okay, so this is the time if you have any questions to ask, even if it is a very naive question, that's fine. So the important thing is that you understand this very clearly. Yes, like I said, Kx, for example, is the mass transfer coefficient on the liquid side. You may want to change the turbulence. Maybe, for example, you can actually have you can increase the flow rate of the liquid flowing down the column by changing the head. For example, if you think about the pressure head at the column, and if you make the liquid column height very high, the hydrostatic pressure will be very high. You may be able to send the liquid at a much faster rates. So when you increase this flow rate, mixing becomes better, the Kx basically improves. Okay, or you could have some sort of a mixing inbuilt, which you can put a kind of an acoustic sensor along the wall, inside the wall, and if you can send an acoustic wave that can create a local mixing along the column. So there are many ways, there are so many ways you can do that. Similarly, if you go to Kx, sorry, ky, which is the mass transfer coefficient for the gas phase. Again, you can think about flow is the biggest component. Okay, how you're going to go to more like a turbulent flow rather than laminar flow, and maybe changing different gas type itself, temperature dependence. So there are so many ways you can actually work with it. So the increase in the column is a different question. So right now I'm talking about one particular location in the column. In fact, the design problem is this: how high the column should be, how what should be the diameter. Okay, in taking into consideration the pressure drop, taking into consideration how much mass transfer we want to effect. Okay, so those are all the design principles we have to address to. But right now we are talking about one single point in the mass transfer equipment, and what is the concentration right there, how much is it away from the equilibrium concentration, because that departure is what the driving force is. If the driving forces are larger, mass transfer rate will be larger. If the driving force is very close to equilibrium point, then the driving force is very small. Okay, so these are very important concepts that we have to understand. So if, for example, like I was saying, I mean, in one of the class I kind of zoomed this particular point, right? If I just zoom in, I showed this interface as a line, and there's a bulk gas phase and then bulk liquid phase, and there is a drop in the concentration corresponding to the equilibrium concentration. Okay, so if you zoom into this particular location here, you will see an interface between the gas and liquid. And if you go to molecular level, you will see that the concentrations are bulk, and then near the interface there will be a drop in the concentration. And so if you imagine it's a mathematical surface, like it's a flat surface with a zero thickness, and you see what is the composition of the gas and liquid in that interface, that corresponds to equilibrium values of x and y. I already said x and y can be not equal to each other, depends on the slope of the equilibrium line. Y can be more than xi, or xi can be more than yi. It depends on the equilibrium line. Okay, so this is very important for us to understand. And then what we are going to do is, equilibrium line we know, driving force line we know. Now what we are going to do, we are going to write a mass balance for the entire equipment. So what comes in should go out at steady state. Okay, now we want to know how that mass balance can be represented in this particular picture. Okay, so in the diagram of y versus x, the equilibrium line is shown, driving force line is shown. Where would the operating line, where would be the material balance line lie? Okay, so that's the aim for us. So what I'm going to do is, I also mentioned that, so here the gas was flowing from bottom to top, liquid was going from top to bottom. So it's called a counter current flow. Okay, so now what I'm going to do, I'm going to start with the co-current flow. Okay, I'll come back to counter current later. So let's do material balance in a co-current process. So what this means is, you have this, let's say you have a weighted wall column. Same design. So liquid in, and this is liquid out. So liquid flows this way. Let's say I pump the gas also from here. So gas in and gas out. So this is what I call as a co-current flow. Both gas and liquid in this case enters in the same place and then leaves in the other side of the equipment. Okay, so the both are entering from the top and leaving at the bottom. This is just an example, but you can think about any other mass transfer equipment which has this kind of a flow condition. Both are entering and both are leaving at the same side. Okay. What I'm going to do is I'm going to just imagine that you can have mass transfer equipment of this kind or many other kind, but we're going to just make it as a black box. Okay, because I'm going to do mass balance, so I'm not interested in the local details of the contact between the gas and liquid, what actually is in the mass transfer equipment. So that is not interest right now, that comes later. So for the purpose of the mass balance, imagine that this mass transfer equipment is shown as a rectangle. Okay, it can be wetted wall column, it can be a packed column, it can be a bubble cap tray, whatever it is. Okay, so that is not important right now. So we will say that the two phases are entering from one side. Okay, we will call this is entry, and the two phases are leaving at the exit. This is the exit point. Okay, whether it should be horizontal or vertical doesn't matter. Okay, this were just for a pictorial representation. So this, so we will assume that this is a mass transfer equipment that allows a contact between the two phases. Okay. Now to make it general, I'm going to use certain notation, and then I'll explain what these notations mean. So here E and R, these are two immiscible phases. So instead of saying gas and liquid, I'm just saying E and R are two phases. Now there is a solute A. This is transferred from R to E. Okay, so solute A transfers from R to E. This is the premise, this is the condition that I'm going to write. You can also do from E to R also subsequently, but if you do this for R to E, E to R is straightforward. Okay. So we got two phases, E and R. These are immiscible. There is a solute A. Okay, and the solute A is a only diffusing phase. Okay, all the other ones are not diffusing. Okay, we are basically talking about A diffusing through non-diffusing other mixtures. Okay, so A is a solute that is transported from R phase to E phase. So here in terms of this notation, R1, this is the total molar flow rate, total moles per unit time. When I say total moles, this means A plus whatever the solvent that it has, the non-diffusing component. Okay, this is in total moles per, and RS, this S here basically denotes more like a solvent like behavior, which is non-diffusing. So this is the moles of non-diffusing solvent per unit time. So these two are molar flow rates. R1 and RS are molar flow rates. If I have to give an example, if you think about let's say R is a gas phase and solute A can be carbon dioxide. Solvent here can be just air. Okay, so if you have a gas mixture of air and CO2, The solvent is basically air, which is not diffusing, but solute is carbon dioxide, that is diffusing. So that's the way that you have to understand. Okay. Similarly, this E1 is the total moles per unit time. This also contains A plus solute of the other phase. Okay, this solute on the two phases need not be the same. Again, example, E phase can be water, okay, and water is non-diffusing, only CO2 is diffusing. So E phase can be a aqueous solution of CO2 water mixture. Okay, yes, there means water, so that is ES. This is moles of non-diffusing solute, non-diffusing solvent per unit time. This is molar quantity. Yes, this also will be which one? Yeah, this would be solvent. Yes, you're right. Yeah, this would be A plus some solvent. This solvent and this solvent need not be the same. These are two different phases. This suffix 1 and 2 means entry and exit. Okay, you can see that 1 is used for the entrance and 2 is for exit. And Y1 would be mole fraction of, this is small y1, mole fraction of A in E phase at the entry. X1 is the mole fraction of A in R phase at the entry point. And Y2, X2, these are equivalent quantities at exit. So going back to this figure again, you can see that I am using a co-current flow. Both streams are entering and each stream is defined with quantities like total molar flow rate, solvent molar flow rate and mole fraction. Okay, you can see that at all the four arrows. Two arrows for the entry of the two phases, two arrows for the exits. So when we do mass balance, we need a control surface above which we write the mass balance. So imagine that you are talking about a control surface shown by this line blue, and here you are going to write mass balance. So what is mass balance? Mass balance is basically how many moles of material is flowing in, and that should be equal to how much is flowing out. So first we will do for the species. Okay, mole balance or mass balance of species A. So from the E phase, you see that E1 Y1 will be the number of moles of solute A entering along the E phase. So E1 is the total molar flow rate, Y1 is the mole fraction. So E1 times Y1 would be the total moles of solute A entering per unit time in the E phase. Solute is also entering through the R phase, that would be R1 X1. Okay, this is the entry point. At steady state, this should be equal to how much moles of A flowing out, that would be E2 Y2 plus R2 X2. So I already said the mass is actually transferred from R to E. Okay, transport is from R to E. Okay, this is important because we want to know where this material balance will lie with respect to the equilibrium line, whether it's going to be above or below. Okay, that's where this direction is important. So if you compare Y1 and Y2, which is the composition on the E phase, how would you compare them? Will they be equal, which will be more or less? How would you compare Y1 and Y2? Y2 will be more than Y1, right? Because mass is transferred from R phase to E phase. So the composition in the E phase will keep on increasing as the mass transfer continues. What about X1 and X2? X1 will be greater than X2. Okay, we are saying intuitively because we understand mass balance has to be satisfied. Okay, if the number of moles is going down in one phase, equal number of moles should be increasing in the other phase. Okay, so we will take this equation and then we will write R1 X1 minus R2 X2 is equal to E2 Y2 minus E1 Y1. Do you think R1 and R2 will be the same? So what is R1 and R2? Let's say go back here. R1 is the total molar flow rate including solute A and the non-solute. R2 is the same quantity but at the exit. Will R1 and R2 be the same? So mass is transferring from R phase to E phase. Total molar flow rate is R1 at the entry. Total molar flow rate is R2 at the exit. How would you compare R1 and R2? Again, R1 is the total molar flow rate including the solute and the solvent. You are comparing these quantities at the exit and entry and exit. Solvent molar flow rate will remain the same because that is not diffusing, so whatever comes in will go out. That's like more like inert material. But the solute is transferring, right? So the molar quantities in the inlet and then molar quantity at the outlet with respect to the solute, this you have to understand, right? So if you have this information, what can you say about R1 and R2? Will they be equal? Which one will be more or which one will be less? What would be? One answer. R2 is lesser than R1. All of you agree? Do you have another answer for this? Okay, this has to be clear. And if I ask the same question about E1 and E2, E2 would be larger than E1. Okay, again we are thinking about intuitively about mass balance. Okay, so this is very important. So we'll come here, we'll recognize that this R1, R2 are not the same. E2, E1 are not the same, and so is X1, X2, Y1, Y2 also. Okay, but even though all the four quantities here, E1, E2, R1, R2, X1, X2, Y1, Y2, 8 of them are there. All of them are changing. However, they will stay in such a way that the right hand side and left hand side here should be balanced. Okay, they can't independently change. Okay, they have to follow this particular mass balance equation. This is what is material balance or mass balance for that matter. Okay, now what I'm going to do is, so this basically is a mass balance equation, but I want to do a little bit of manipulation of this equation, and the advantage of this will become evident as we go along. Okay, so let's say what is X1? So X1 is the mole fraction of solute A in the entry point in the R phase, right? So this can be written as R1 minus Rs by R1, isn't it? R1 minus Rs will be the total molar flow rate of the solute A only at the entry. Okay, R1 is total, Rs is only the solvent. The difference would be the solute molar flow rate. Divide that by the total molar flow rate, which is R1. So that should give you the mole fraction X1, right? Right? So what we are saying is, for the entry point, we define three quantities: R1, Rs, X1. Okay, but these three are not independent quantities. They are related, right? So that relation is this: if I know Rs and X1, I can find R1. If I know R1 and X1, I can find Rs. Okay, even though there are three quantities, only two of them are independent. The third one is actually defined by this relation. Okay, and similarly, I can write R2 as Rs by 1 minus X2. I am able to write this only because Rs is constant, Es is also constant, because that is the solvent flow rate that is not participating in the mass transfer. They are only acting as an inert carrier for the solute. So what I'm going to do is, in this mass balance equation, I'm going to replace R1, R2, E1, E2, all of them with respect to the solvent flow rates, Rs and Es. Okay, so this equation now will become so if you look at this particular modified equation, you see that the mole fractions are entering in a specific combinations. Mole fraction by 1 minus mole fraction, x by 1 minus x, y by 1 minus y. So because that form is retained in all the terms, maybe it's a good idea to define a new variable to replace x by 1 minus x. Okay, so I'm going to use a new variable capital X. This I'm going to call it as x1 by 1 minus, so well I'll just define 1x x by 1 minus x, and capital Y as y by 1 minus y. If x is a mole fraction, small x is mole fraction, this capital X is actually mole ratio. This basically means moles of A divided by moles of the solvent or solute free component. And similarly, Y is also here mole ratio. So we are basically defining a quantity which is called mole ratio, and we are going to replace this mole fraction with respect to mole ratio. And even though we change this, but from here we can also change the two units interchangeably. Given in small x, you can convert into capital X, or given in capital X, you can convert to small x by this simple relation. Okay, so small x is mole fraction, capital X is mole ratio, and similarly for small y and capital Y. So with this definition, I can take this equation and I can write Rs x1. Note that I am using capital X now. So from here I can rearrange this equation as y2 minus y1 is equal to minus Rs by Es into x2 minus x1. So this is basically an equation of a line, equation of a straight line. with a slope of minus Rs by Es. Here I used 1 and 2 as a two points at the entry and exit. Okay, so instead of exit point, if I take a particular point here somewhere, okay, so let's say I do only mass balance in this loop, okay, and somewhere along this point in this particular maybe I'll just do it differently so that it is at one particular location. Yeah, okay, let's look at this purple envelope, and if I do the mass balance at this particular envelope, it will be exactly the same, except that instead of y2 x2 I should be using the value of y and x here. Es anyway is constant at any point. Okay, so if I do this at any point in the equipment, it would be y minus y1 is equal to minus Rs by Es into x minus x1. Okay, so this is what is called the operating line. So what this basically says is that the way in which the composition will change along the mass transfer equipment, that has to follow this particular line. That's what this means. Okay, so let's say you're looking at the entry point, co-current entry point. Okay, so here one phase will be rich in solute A, other one will be leaner. When you go a little above, if you go a little inside the mass transfer equipment, the solute transfer would have happened. Okay, one phase would have decreased its composition, another phase would have picked up the composition. And if you keep on looking at these points of compositions on both phases along the length, that will be this particular line, where y1 x1 are the inlet compositions and capital X capital Y are the composition inside the mass transfer equipment as you go inside. Okay, since Rs and Es are the solute free molar flow rate, the solvent flow rate, they are remaining constant throughout the operation, and that slope Rs Es is going to be also constant because Rs and Es are constant. So this is going to be an equation of a straight line with a constant slope. Okay, now it is clear why we are using molar ratio as the quantity. When we cast this material balance in a mole ratio based composition, the operating line comes out as a straight line. Okay, if you go back here, the actual mass balance I was showing here, the fact that R1 is changing, R2 is changing, X1 is changing, X2 is changing, Y1 is changing, Y2 changing, this cannot be cast into a straight line, it will be a curve. We are not changing the information, we are only casting this equation in a different unit system so as to show the mass balance as a straight line. For that, we are doing two things. One is we are expressing everything in terms of the solute free molar flow rates Rs and Es, and the compositions are now written in terms of mole ratios instead of mole fractions. With these two modifications, we are able to cast the mass balance equation, material balance equation in terms of a straight line. Right? Do you follow? Okay. So we have a few more minutes. Let me just go back and review this again. So what we are trying to do is we have a mass transfer equipment where two phases are flowing in, two phases are flowing out, and the mass transfer is happening. So we are considering a particular flow condition where both the fluids are entering in the same direction. It's a co-current flow. Okay, in the co-current flow, we are trying to write a mass balance equation, and the mass balance equation is very simple. It's basically how much mass is going in and how much mass is coming out. Only change we need to do here is we are going to replace the molar flow rate R1, R2, E1, E2 in terms of the solute free molar flow rate, which is the solvent flow rate. Okay, that is RS and ES. So these are the set of equations that relate the molar flow rates to the solvent molar flow rates. So once you substitute that, you get this equation where the compositions are in a particular form, like x by 1 minus x, y by 1 minus y. And then we define a new set of coordinates, a new set of variables, capital X and capital Y, which are mole ratios. When you write the mass balance in terms of mole ratios and rearrange, you get an equation of a straight line representing the change in the composition of the fluids as you go from the entrance to exit. Okay, is it clear? This Y and this X, suppose if I say, so if I go from, let's say this is my mass transfer equipment, and let's say I define some variable L denoting the location. So when L equal to 0, it is entry. When small l equal to capital L, exit. Okay, then what we are saying here is this equation y as a function of L minus y1, which is constant, minus Rs by Es, x as a function of L minus x1. This is what we are saying. Okay, this x and y will be a function of L. As you go into the mass transfer equipment, the composition is changing. The change in the composition must follow this particular mass balance, which is a straight line. That's all we are saying. Okay, so we'll stop here. Next class, what I will do, I will go back here, the this particular diagram. I will show how to represent the mass balance or the operating line into this diagram. Okay, so essentially in the entire course, we'll be dealing with the three kinds of lines: equilibrium line, driving force line, operating line. These three are very important because in the design principle that we looked at, we wanted to know how much contact time should be given, how long the mass transfer equipment should be, what should be the length of the packed bed. Okay, all the questions will be answered by considering the three things: operating line, equilibrium line, and the driving force line. Driving force line is manifested by the rates of mass transfer. Operating line is manifested by the mass balance. Equilibrium line is manifested by thermodynamics. And you can see the nice marriage of all these concepts putting into together. And the graphical representation is one nice thing because it actually allows you to see everything in one place graphically. Okay, so that way the graphical representation of three lines and the relationships are so useful in going forward and designing these operations. Okay, so we'll stop here.